Okay, so welcome to the Unit 5B Lesson 1 on graphing radical functions. In today's lesson, we are going to look at graphing the inverse of quadratic and cubic functions. And we're going to then look at that and kind of identify the parent functions for square root and cube root functions. And then we're going to graph some square root and cube root functions using transformations. All right, so a lot of graphing today. Let's begin with just graphing our parent functions of the quadratic function. All right, this function here, f of x equals x squared. So we'll start here by picking some x and y values. And I'm just going to pick -2, -1, 0, 1, and 2. We plug those x values in to this function, and we get 4. 1, 0, 1, and 4. So from those points, we can graph f of x equals x squared. And we'll just draw that graph in there. And it looks something like that. And that's the function f of x equals x squared. So we can do a little bit of analysis, talk about our domain and range. The domain of this function would be -infinity to infinity, and then the range of this function would be 0 to infinity. Remember, you'd use a bracket there because 0 is actually a y value. It is included in the range. So that's our function f of x equals x squared. We can then look at the graph of g of x equals x to the third, and we could again pick x values. We could say -2, -1, 0, 1, and 2 to get -8, -1, 0, 1, and 8. So with those x and y values, we can graph over here. We go down over 2, down 8, which is a little bit off our graph, -1, 1, 0, 0, 1, 1, and 2, +8. So we kind of get this general curve here, right? And we can talk about the domain and range of this function, which we would get -infinity to +infinity as well. And the range would be -infinity to infinity. So those are the two kind of functions where we can talk about inverse functions. And we remember from previous units that the inverse of a function, right, if this is f of x, then the inverse of f of x will switch x and y, right? So our points become 4, 1, 0, 1, and 4. And then we get -2, -1, 0, 1, and 4. So if we were to graph these points, right, if we go to 4 and then down to -2, 1, -1, 0, 0, 1, 1, and then 4, +2, we would get something that looks like this, right? So we would see that the inverse of the function f of x equals x squared. The inverse is not a function. This is not a function. The inverse is not a function. It's still an inverse, but it's not a function because it fails the vertical line test. So the inverse of a function is not always a function, but it is still an inverse. All right? So what would happen if we did if we switched this over here and we did the inverse of this function? We would get -8, -1, 0, 1, and +8, -2, -1, 0, 1, and +2. So if we were to do this, we would get something that looked a little bit here. These 3 points would still be true. You get something way out here. The curve would make it look a little different. And we have here. Now, the inverse of the function g of x equals x cubed is a function. This is a function. So in this case, the inverse is a function as well as the original being a function. All right? So, kind of apply what we're talking about here to the domain and range of inverse functions. So, if the domain of the original function was negative infinity to infinity, then that will now become the range of my inverse, right? And I'm just going to cross this off because it's not actually a function, right? Let's look at the inverse. And then the domain would become the range. So from 0 to infinity. And that makes sense because the x values are restricted in this first case to 0 and greater. Domain and range here, it's not really going to be a noticeable difference because they're exactly the same, but they also change positions as well. Okay? So this kind of gives you a little bit of an idea about inverses again, right? We could talk about finding inverses algebraically, right? So we started off with f of x equals x squared, and now we're going to talk a little bit about the inverse of that. So first thing we do is switch f of x to y, and then we're going to switch x and y's positions. Well, in that case, right, we get x equals y squared. We would take care of that by taking the square root of both sides, and we would get y equals plus or minus the square root of x. All right, and that would be the inverse. We'll switch it back to inverse notation. We can do the same thing with g of x, x to the third power. Switch that to y. Switch x and y's position. And then we would solve for y by taking the third root. So y equals the third root of x, right? The third root of x. Let's get a little better. Okay, and then we switch it back to inverse notation, and we get the third root of x. Okay, so going back and talking about how to find inverses graphically, talking about the impacts of how it impacts the domain and range of the functions, and then how to find the inverses algebraically, kind of brings us to the new types of functions we're going to be talking about. Now, we're going to now look at radical functions and the parent functions of those radical functions. The one thing we have to do here, though, is restrict. We're now going to restrict this, right? So, and we're going to restrict this, right? So now we're going to look at the function f of x equals the square root of x. And now in this case, because we're restricting it a little bit, we are not going to talk about negative square root of x. We're talking about the positive square root of x only, right? But we also can kind of use the idea of flipping the inverse, right? So I'm going to talk about the change in x and the change in y. I'm picking x values that I know I'll be able to take the square root of. So 0, 1, 4. I picked perfect square roots so that when I plug that in, the square root of 0 is 0. The square root of 1 is 1, and the square root of 4 is 2. So this gives me some nice, easy points. Could I have picked the square root of 3? Yeah, but I really don't want to graph that. All right? So if I'm going to graph this, it'll be 0, 0, 1, 1, and 4, 2. Now, because my domain, right, the domain of this is restricted to 0, to infinity, when I draw this, there is only an arrow on the right-hand side. This left-hand point, the starting point of 0, is going to be just a dot, right? This would give me a range of 0 to infinity as well. Okay? And this is the parent function of the square root of x. All right? This is the parent function for the square root of x. The next thing I'm going to look at here is the parent function, and we'll call this g of x, for the parent function, the cube root of x. Now, because it's an odd, we don't have to make any restrictions on the domain and range. It'll be negative infinity to infinity. But again, when I pick my values, I'm going to pick nice, easy values that I can take the cube root of. So again, I'm going to pick negative 8, negative 1, 0, 1, and 8. So that when I take the cube root of negative 8, I get negative 2. When I take the cube root of negative 1, I get negative 1, 0, 1, and 8, etc. Sorry, not 8 there. 2. Square root of 8 is 2. Cube root of 8 is 2. All right, so let's graph this. We go back negative 8, down 2. It's that same graph we kind of looked at the top. We're not going to have any restrictions, so it's just going to look is the true inverse of x to the third power, right? No restrictions, no changes had to be made to it. That is the parent function. So the way I'm going to show you to graph these is by a transformational kind of approach. And again, if you notice, I use this delta x notation, delta y, which means change in x, right? Delta means change, right? So the way that I'm going to approach this, right, I'm going to key in here on these key points, right, which is kind of like, these are my key points, this one and this one. So I'm always going to be referring back to that point when I talk about my change in x and change in y. All right, those are my kind of my new origins, right? That's the origin point, right, for both of these. All right, so that's going to shift, and then we'll take a look at it. All right, because our last step in the process today is to talk about these transformations. And here's kind of all of our transformation notation here, right, which is very similar to the transformation notation we use for square roots and for quadratics and cubic functions that we use for absolute functions so far this year. So let's take a look at what we're talking about here. What's nice about this is we're always going to approach this in the same way, right? This is a square root function, so I'm always going to pick the same x, y values of 0, 1, 4. And then this is always going to be 0, 1, 2. All right? And in fact, because it's always 0, 0, I don't really even care about that point anymore. That point is going to get transformed by these, right? So this is going to identify my starting point. So this is right 1. This is up 3. And here we have a reflection. And I'll show you what to do with the reflection in a second. All right? But again, the right 1 up 3, my origin will move right 1 up 3. So there is my starting point now. All right? That's my key point. Now, because it's reflected, that's a multiplier, right? So all of these are going to be multiplied by negative 1. So that'll give me negative 1 and negative 2, right? So my change in x is right 1, down 1. So from my starting point, I'll move right 1, down 1, and then I'll move right 4. 1, 2, 3, 4, down 2. And there is my function, graphed. I can talk about my domain. My domain will include 1 to infinity. My range, since my arrow is down, going down, it would be negative infinity to the highest point, which is 3. Okay? Let's kind of see what you would do with a cube root. Let's take this, again, delta x, delta y, and we're going to pick negative 8, negative 1, 0, 1, and 8, negative 2, negative 1, 0, 1, and 2. Again, we don't care about that 0, 0. This is going to be right 2, and this is stretched by 2. Okay? So right 2 would put me right here. And now this stretching by 2, again, this would be a times 2. All these points are times 2. So negative 4, negative 2, 2, and 4. And the originals are now gone. So I'll start at my original point, go backwards 8, 1, 2, 3, 4, 5, 6, 7, 8, down 4. So that would put me right there. I would go backwards 1, down 2, and that would be right there. I would go forward 1 and up 2, and then forward 8, up 4, which would put me somewhere about right there, right? And then we'll kind of just draw our graph to make it look something like that. So I hope you can see kind of how that delta movement can help you with just plotting the points, right? Again, the focus here is on these key points here, and then doing the movements, right? These are movements. Those are not coordinates. They're how to move from your central point. Our domain would be negative infinity to infinity. Range, negative infinity to infinity. Okay, so go ahead, pause the video, and attempt these next 4 questions, or at least attempt the next 2. Try to graph these, and then unpause the video, and I'll have the correct graph up, and you can check your work. But do try this on your own. All right? Okay, here's the 2 graphs with the domain and range that you should be able to have gotten correct so far. All right, so the last questions here have to do with if we give you a graph and we ask you to write the equation for the graph shown, you should be able to do this. Now we want to assume that the graph is going to the right there and that this is a point. So I know that if it has a point going in one direction, this is going to be the square root of x. That's my parent function. So understanding that, I can start to think about what's happening here. So it looks like those are my key points, negative 2 and negative 3. So I know it's the square root of x, and if it's left 2, it'd be a plus 2, and down 3 would be a negative 3. Now it's going down, so that's a reflection, and then kind of thinking about whether or not it's been stretched. So the normal movement's over 1, down 1, and that looks like it's over 1, down 1. So we'll assume that that's a 1. All right? Now, go ahead and pause the video and attempt number 6. And here's the graph for number 6. As you can see, it is a cube root function. So make sure that you put that index of 3 on your radical so you don't lose points by calling it a square root. All right? And that's the notes for today on graphing and a review of inverses of functions. So hope you found this interesting. We will be exploring the classwork next time we see you in class. Have a great day.